Hello, this video will cover section 4.1 of the chapter for exponential and logarithmic functions. The title of our section is called Exponential Functions for section 4.1, and this is for the class of Math 1324. So let's just start by looking at some examples of exponential functions. But before that, let's look at something that is not an exponential function. And we finished in chapter 3, we finished covering polynomial functions. And so polynomial functions, for example, a quadratic function is a polynomial function. One characteristic of it is that all of the exponents are non-negative integers. That means that they could be positive numbers or they could also be zero. And that will be the we could call it the exponent of the variable that goes attached to our constant term, in this case, the -4. So in this case, this polynomial function, we say that it is of degree 2 because it is the highest exponent. And here the independent variable, which is the x, that one is not the exponent. And so just to clarify this one, we call it quadratic function, and it is from the family of polynomials. Now in this section, we're going to start working with exponential functions, and then we're going to make our way to logarithmic functions. So the ones that we see here, they are exponential functions. And we can have here 10 to the power x. So 10, the big number that is raised to the exponent, is what we refer to as the base. That base will have to be a positive constant. And because of that, we say that it will be greater than 0. Now here, I want to add something. That base cannot equal to 1. And that is because if we had a function like this, 1 to the power x, and if I was to create a table of values for x and y, and let's say I make my x a -2, a -1, a 0, a 1, and a 2. These are common x values, not that they're the only ones we can use, but I just like to choose stuff on the left and the right side of 0. So in this case, to find the y value, we will have to substitute the x values that I gave you for the exponent, and that will be 1 to the power x. So in this case, we'll have 1 to the power -2, 1 to the power -1, 1 to the power 0, 1 to the power 1, and 1 to the power 2. Now, if you don't know how to deal with negative exponents, I will recommend that you watch that video from my YouTube channel. But right here, with positive exponents, or even this one, 1 to the power 0, is just equal to 1. And so is the case for 1 to the power -2 and 1 to the power -1. So if we were to plot all of these points here, we will end up with all these points going across y equals 1, but with a different x value. And so if we connect them, we will get not an exponential function, but this is in fact the equation for the line y equals 1, which is a horizontal line. And if you remember, horizontal lines are functions. They do pass the vertical line test. You can see that. So therefore, they are functions. And moreover, we called it the constant function because it is not increasing nor decreasing. And moreover, is y equals to a number, a constant. So just from this statement for exponential functions, we want the base to be greater than 0, but also we need to exclude 1. Now, going back to our examples, here function g is another example of an exponential function. And here the independent variable, also for 10 to the x, the independent variable will be the exponent. That will be the x, the input. Now here the base is 1.05. For the next example, function h of x, the base is 3, the big number, and then here we have 0.6x. So you could see there that is also exponential. X is being, the independent variable is being in the place of the exponent. Now the next one, it doesn't look like exponential at first sight because we have x squared, so we might be thinking that's a polynomial. But the fact that that negative x squared is the exponent of the base 2, that makes it also be an exponential function. So those 4 are all exponential functions. This one is not. That is a constant function. Okay, so now we're going to grab one of the most common examples of an exponential function, and that is 2 to the power x. So for that, we have some x values already assigned here. And so what we're going to be doing is substitute the x value into the equation. So 2 to the power x. Now from there, we're going to be finding some points, x comma y, and then we're going to graph them. So for our first example, f of -3, this will be 2 to the power -3, which is the same as 1 over 2 to the power 3. And this is one of the rules that we have with exponents. And that you can bring that, you can picture it as switching places with the numerator and the denominator. And so this exponent from being negative, once we bring the base of 2 to the denominator, it will take care of the sign of the exponent, turning it negative. So just to finish this one, and I'm actually going to need more space. This will be 1 over 2 to the power 3 is 2 times 2 times 2, so it will be 1/8. And so as a point, we're going to have the point -3 for x and 1/8 for y. Now the next number, we have f of -2. So this will be 2 to the power -2. Now I'm going to use the same idea. So I'm going to have 1 over 2 squared. And so that will be 1 over 4. So from here, we will get the point -2 comma 1/4. So our next x value is -1. So here we will have 2 to the power -1. And this will be 1 divided by 2 to the power 1, which it will just be 1/2. From here, we get the point -1 comma 1/2. Next one, we have f to the power 0, and so that would be 2 to the power 0, which is equal to 1. And from here, we will get the point 0, comma 1. Next one, f of 1. So we will be substituting the x, the exponent x with the number 1. So 2 to the power 1 is just 2. So we get the point 1, comma 2. And we have 2 more to go. 2, f of 2 will be 2 to the power 2, which will be 2 times 2, which is 4. So the point is 2, comma 4. The next one, we have f of 3, and that will be 2 to the power 3, which is 2 times 2 times 2, and that will be 8. So we get the point 3, comma 8. Now we're going to use those points that we found, and we're going to plot them in here. So we could see clearly that this point, since the x value is 0, is going to be on the y-axis. Therefore, we can go ahead and call it our y-intercept, because it is on the y-axis. Now, the next point, I like to graph the ones with positive numbers, the ones that don't have fractions, I should say. So I'm going to graph 1, comma 2. So that will be here. And then I'm going to graph 2, comma 4 here. And then I'm also going to graph 3, comma 8. So it will be there. Now I'm going to deal with the negative ones, with the negative x value. So -1 and the y value is 1/2. The next one is -2 for x and the y value is 1/4. And -3, 1/8, of course, is very hard to graph, but what I'm doing is just getting close to my x-axis. However, I will never touch the x-axis. And because of that, we could say that we're going to have a horizontal asymptote, just like rational functions had, most of them have a horizontal a horizontal asymptote. So in this case, the equation, and we could consider this function one of the parent functions. So the horizontal asymptote will be the equation y equals 0. And that is standard for the parent functions. Let's go ahead and write down what the domain and the range will be. And so the domain, remember, those are the x values that this function could take. You can make the exponent be 0, positive, negative, a fraction, a square root, whatever you want. So the domain is going to be all real numbers. Remember, those are the x values. Now, the range, the outputs that this function will give you, they are all going to be positive numbers. In fact, this function grows exponentially. We also refer to it as exponential growth. And you can see clearly that it is increasing. And the smallest y value is going to get closer and closer to 0. However, it will never be 0. And therefore, we have to use parentheses because 0 is not included in the range. We could try, and I believe there's a question here, 2 to the power 50, it says here. So to estimate 2 to the power 50, we could enter that on the calculator. And in fact, it's a very big number. Imagine the number 2 and multiply by itself 50 times. And so that will give us, I'm going to write the number first. So I believe it's 2,961,647,482. So if that was the height, the output being the height of that graph for that particular point, it will be 2,961,647,482 units high. So of course it will be impossible for us to graph it. We do care about these exponential functions because a lot of things that happen in our world could be modeled with an exponential function. And we could talk about things, examples in science, such as bacteria growth or exponential decay, such as calculating. Some of you will be taking chemistry, and you will have to calculate the half-life of certain element, or perhaps the half-life of some human remains. And I shouldn't say half-life, I should say more like the age of some human remains, such as anthropologists do. Some other interesting equations we will look at will be logarithmic equations, but those will not come until section 4.3. All right, so right here we already established the base. Whenever the base, well, we haven't discussed that, but let's do that. Whenever the base is greater than 1, then the function will be increasing And remember, we always read our graphs from left to right. Okay, so now we're going to move on to the next slide. And here we're going to graph 2 to the power negative x. Now, before we construct the table, we're going to rewrite the function of function g, the equation of function g, so that it has no negative sign in front of the exponent. So remember, if we have 2 to the power negative x, we assume that the denominator is a 1. And so what I can do is just replace, or not replace, but interchange the numerator in the denominator, and that will take care of the negative sign of the exponent. So it will be 2 to the power, 1 divided by 2 to the power x. So now we're going to graph it. And of course, we're going to need our equation with the positive exponent now. So for the first one, we'll have g of negative 3. So in this case, we will have 1 divided by 2 to the power negative 3. Now, I don't want that exponent to be negative, so now I'm going to bring it back to the top, to the numerator. So it will be 2 to the power 3. I could bring the 1 down here, but it's not really necessary. So 2 to the power 3 is 8. Now, for g of negative 2, we will have 1 divided by 2 to the power negative 2. And so that will be 2 to the power positive 2. So that will be 4. And here, so on, let's go ahead and write our points so we don't forget about that. So first we got the point negative 3, 8. And then we got the point negative 2, 4. So here, moving on, g of negative 1, and so that will be 1 over 2 to the power negative 1. So this will be 2 to the power 1, and so that is 2. The point that comes from it is negative 1, 2. Next, x value to substitute is 0. So we got to find 1 over 2 to the power 0. So 2 to the power 0 is equal to 1. So we have 1 over 1, which is equal to 1. And here we have the point 0, 1. Next x value will be g of 1. So 1 over 2 to the power 1, it will be 1 over 2, or just 1/2. So 1, 1/2. Next one, it is g of 2, and so that will be 1 over 2 squared, which will be 1 over 4. Next one is g of 3, so that will be 1 over 2 to the third. This is a 3, and so that will be 1 over 8. Let's write down our points. So we have 2, 1/4, and then we have 3 for x and 1/8 for y. So we're going to go ahead and graph it, graph those points. Now it's important to notice that the y-intercept is actually the same, 0, 1. So let's start from there. That will be this point here. And let's graph this one. So negative 3, 8. And it will be positive 8. Then we have negative 2, 4. We'll have negative 1, 2. And then we have 1, 1/2. 2, 1/4. And 3, 1/8. So now if I connect these points, and I have to be careful to not touch the x-axis. So they do go like that. And so we also have the same horizontal asymptote. So it doesn't matter how large our x values get. If our function is this, and let's say we make we want to make x a 50. So this will be 1 over 2 to the power 50. And from our previous problem, we know that that's going to give us a pretty big denominator. It's going to be something like 1 over, and that was something like 2,961,647 thousand, and then 482. And so that number, it is very small because it has a very large denominator. However, that number is still positive. And it doesn't matter how big we make our x value, the fraction that we will get or the decimal that we will get, it will still be positive. It will not be 0. So the domain of this function is the same as the previous one, negative infinity to positive infinity. However, the range, actually the range will be the same too, because the smallest possible y value will be anything that is greater than 0. So we will say from 0 to positive infinity, but of course not including 0. This function, if we read it left to right, we will say that it is exponential decay. We could also say that it is decreasing. And in fact, remember that problem that we did with the value of a car? The value of a car does not depreciate as a linear function. In fact, the value of a car depreciates exponentially. Every year, it will go down more and more and more and more until it's virtually 0, but it will never be 0, and it will never have a negative value. Now, let's compare these two graphs. So the very first one, 2 to the power x, oops, and I lost the image, but I can graph it for you. 2 to the power x was a graph that was increasing like that. And that is because we had a base that was positive. The base is 2, which is greater than 0. That means that is positive. So whenever your base is greater than 0, you will have exponential growth. Now let's look at the other one. And for this one, we had a graph that was decreasing. And if you recall the equation for it, we started with 2 to the power negative x, but we transformed the equation into 1 over 2 to the power x. Now that equation is similar to this, 1 over 2 to the power x. So in this case, we can say that the base, which is equal to 1/2, it is less than 1, but it's also greater than 0, meaning positive. So if the base was greater than 1, like example 1, we have exponential growth. And whenever the base is less than 1, but still positive, meaning greater than 0. And so we're referring to all those numbers that will be on the number line here between 0 and 1, all those little tiny decimals. And so if that is the case, then we will have exponential decay. Moreover, the comparison of the two graphs, I'm just going to graph the other one here. The one that we started with, Imagine this one in red is 2 to the x, and the one in black is 1/2 to the power x, or we could also call it 2 to the power negative x. So the relationship between those two is that there are reflections of each other across the y-axis, the one that we have here. And that's it. Well, also it's important to notice that if we're talking about exponential decay, the smallest the base, the steeper the decrease. So in this case, 1/10 is way smaller. 1/10 is smaller than 1/2, right? So if the base is smaller, the function will be decreasing at a faster rate. Now, going back to the previous slide, this one shows us that whenever the base is greater than 1, the bigger the base, the steeper the increase will be, such as the case here. If you compare 2 to the x and 10 to the x, you can see how the function 10 to the x, it's growing faster. So we cover example 1 and 2, and this is the end of the video. If you would like to watch the next problems, I do have videos on my YouTube channel that cover examples 3 and 4. There's another one for 6 and 7, and I'm not sure, but you're welcome to look at it. So thank you for watching. Don't forget to do your homework.